So is there an atmospheric CO2 thermostat? Obviously depends on the time scale. We will revisit some of the details here in terms of starting with the URI reaction, which is basically about the weathering of silicate rocks, which have a general composition of this type, CaSiO3, and then you have carbon dioxide dissolved in water, carbonic acid, weathering the rocks over geologic timescales to produce calcium carbonate, which is going to wash out with the river runoff into the oceans eventually and release SiO2. David Archer says we can strip the SiO2 from both sides, which I'm sure geologists will not like very much, and reduce it to CaO plus CO2, giving us CaCO3. And calcium carbonate is an important part of the whole carbon cycle. It is obviously something that is now used for calcifying organisms like the coccolithophores, forams, foraminifera, coral reefs, and so on and so forth. And it precipitates out, and how much makes it to the bottom gets buried and then gets converted into limestone and so on, and then eventually gets exposed by plate tectonics and gets again weathered and re-releases CO2 and so on. So there is lots of these activities going on which involves physical system, biological system, terrestrial ecosystem, marine ecosystem, and CO2 running through the whole thing, including geologic processes like mid-ocean ridges, subduction, and so on. So is there really a CO2 weathering thermostat, and is it just a coincidence because plate tectonics and things like the Himalayan mountain formation, monsoon evolution, a new exposed material weathering down and drawing down CO2. So those are slightly different processes than these weatherings. But there are nice papers by people like Zeeby, what's his first? Richard Zeeby, I think, from University of Hawaii, which look at various timescales like the Vostok ice core and argue that indeed such a thermostat exists. So that's kind of an indication that is derived from this that we looked at before, the Vostok ice core record, which shows the abrupt deglaciations that we talked about because of the ice albedo feedbacks, and we had CO2 also acting as a positive feedback on this, of course, and a slow deglaciation, a slow glaciation because of the cooling of the atmosphere, reduced humidity, reduced snowfall rates, and so on. So you have not so abrupt warming here, slower the glaciation, abrupt warming, and so on and so forth. But the idea is that there is a certain bottom and top of this variability of CO2 at glacial, deglacial cycles. We talked about 100 ppm change. We also said we don't have a perfectly good theory to explain the exact change that is happening, but we in general know that when glaciation happens, terrestrial biosphere is shut off, oceans are shut off to a large extent, CO2 exchange is reduced, weathering is reduced, but volcanic activity, for example, continues to build up CO2 in the atmosphere. And the glacial times tend to be drier, more dust, which could potentially put more aeolian iron into the ocean, which turns out to be a micronutrient which can enhance photosynthesis in the ocean and increase drawdown of CO2. All kinds of hypotheses exist, how much shelf area is exposed, what it does to the phosphorus cycle, which is another critical nutrient for the marine phytoplankton photosynthesis, and so on and so forth. But the main story again is that there seems to be some sort of a stable geologic timescale carbon cycle and a CO2 thermostat. And of course, why are we worried about? Because right now we are increasing CO2 at a very fast level. We are way above anything that has been seen for a long time. So what does that mean in terms of the climate response? This is what we are mostly worried about. So we need to understand how carbon behaves, and then, which means what? which means if we increase CO2 like this, how long is it going to take it for to equilibrate the system? We will see an example from the past. Plus, what kind of climate sensitivity is there? So we know the warming and the cooling that happened on the glacial, deglacial timescales, but when we kick the system out of this range and put it into a new regime like this, how fast will the atmosphere respond? That's called climate sensitivity, which we will look at. Okay. So what is the other side of this weathering and drawdown of CO2? It's the degassing of CO2 from the earth, of course. So when the calcium carbonate that is generated by weathering of the silicate rocks going in this direction is creating, and that's washing off into the ocean, there are calcifying organisms, and there is sinking of calcium carbonate, which over time is going to be metamorphized into rocks, which are going to be exposed either through plate tectonics like the Dover cliffs with limestones, or at the mid-ocean ridges where new ocean crust is being formed and calcium carbonate is getting exposed, and we are going in this direction to release CO2. So this is metamorphosis and rock formation and CO2 release, and that's the calcium carbonate getting weathered again by shortening this reaction by removing the SiO2 from both sides. So there is a rock formation, and then there is weathering. So CO2 release and CO2 uptake, right? The CO2 weathering time scale is now known to be about 100,000 years, whereas these other reactions are longer time scale. Right, so we have to always remember the time scales involved. So this is a simple way of saying it. I'll show a couple of other figures which show some more details. So here you have mantle input mid-ocean ridges where CO2 is being released, and that is ocean carbon cycle and so on, creating burial of carbonates and organic carbon. So this is the biological and this is the carbonate cycle. So calcium carbonate and organic carbon. We will see that the ratio of the calcium carbonate and organic carbon in the sediments is almost a constant, 1:4. So there is some kind of regulation there as well. And of course the weathering, carbonate weathering and oxidative weathering is happening as well. So this is taking up oxygen, and this is taking up CO2. So this is oxidative weathering, and this is carbonate weathering. So there is a oxygen thermostat involved as well. So carbon cycle and oxygen cycle, it turns out, that are closely coupled together. So this is another way to look at it. New ocean crust is always being formed at mid-ocean ridges, like the Atlantic one, that's well known. Pacific has many, Indian Ocean has a couple, and so on. So you have the mantle over which the crust rides, and then rigid mantle material is going to be broken through, and the spreading happens here, and there is subduction and calcium carbonate burial and CO2 burial happening, as well as metamorphosis, silicate rock formation, and emission of CO2 through the volcanic activities. And so you are forming igneous rocks, continental granitic crust, and oceanic basaltic crust. This tends to be lighter, almost 30% lighter, also lighter in color. This tends to be heavier, darker in color, and it's much more compressed and much less deeper. This is much more wider. I think that you can look up the numbers, several. So this is overall 750 kilometers, but this is something like maybe 30 kilometers to 300 kilometers or something we can look up later. Okay, so this is another way to look at it. This is from a science paper. Somehow it got cut off. Geologic sources and sinks of CO2, so it's easier to look at. The oceanic arc CO2 degassing that we talked about, that happens because of these subduction processes, and there is CO2 from the hotspot volcanoes like Galapagos and Hawaiian Islands, where the magma is coming out through the middle of the plate. So solar radiation, as well as the differences between sinks and sources of CO2, contributes to the state of the climate. If a sink term such as weathering of ophiolite complexes increases, the system shifts to lower atmospheric CO2 concentration because there is more drawdown, as the CO2 weathering thermostat that we talked about. This may lead to a period of cooling with glaciations that we also talked about. So energy balance on very different time scales is what we are talking about. There is the mid-ocean ridge again that we talked about. So mantle CO2 is degassing here, and we are burying organic carbon, which is basically phytoplankton photosynthesis, which is not consumed or respired and makes it to the bottom. It tends to be very, very small. Even in the strong upwelling productive regions, only about 1% makes it to the bottom, but the less productive regions, much less than 1% would make it to the bottom. And then there are calcium carbonate formers, phytoplankton diatoms. They form silica cells, but nonetheless, reefs and so on. So there is burial of calcium carbonate and organic carbon, and there is the formation of ophiolite and subduction, and this spreading of the formation of the ocean crust and the rate at which happens also decides the sea level changes, and there have been large sea level changes over geologic timescales, which we don't completely understand, but are probably related to the rate of crust formation and spreading and subduction and so on. So there is continental arc and CO2 degassing, oxidative weathering, also a source of CO2, and metamorphosis of carbonate rocks liberates CO2. So all these are sources and sinks, and obviously biology is a story. On land, it's the formation of coal that we talked about, and we will see again later on that terrestrial vegetation, especially about 400 to 300 million years ago, also drew down so much carbon through photosynthesis that it may have led to a snowball Earth episode, which means a very large scale freezing of the Earth, maybe down into lower latitudes. There is controversy about it, how actually glaciation could happen all the way to the tropics, and whether, if that happens, how biology would have survived, because if ocean is covered, then how would light penetrate for photosynthesis and so on and so forth. But along the way, these calcifiers that we already mentioned, like forams and coccolithophores, they only evolved more recently. They are now part of the calcium carbonate precipitation story, and this shows the geologic timescales here, 300 million years, and it's showing pelagic calcifiers, Cretaceous, Paleogene, around let's say 60-70 million years ago. And there is another transition somewhere about 170 million years ago. And then there are these mass extinction events of the Triassic, Jurassic, Permian, Triassic, and so on. So there has been this marine biological cycle evolution. So dinoflagellate cysts, which do not survive, they are soft and they don't have hard shells. And then hard shells, as you can imagine, probably evolved as a part of a strategy to protect against being eaten by somebody else. So you can see that there is a combination of predator frequency of predation traces happening. So this is the predation and defense that is being looked at. So predation is higher here, and then predation goes down, defense mechanism dominates, and you have pelagic calcifiers dominating. the basic story is that the calcifiers are a recent evolution. Now they are part of the calcium carbonate story and carbon cycle story, but they also themselves have depended on sea level changes on the long time scale, either because of the plate tectonics. When you go back long enough, obviously the continents were distributed differently. So here we are looking at a longer time scale, 400,000 year time scale, and sea level changes happening on those time scales using benthic 4M delta O18, which you haven't explained. We will explain in a minute. But just looking at the last ice age, Pleistocene ice ages, 20,000 years ago you had extensive glaciation with glaciers coming down into North America, Europe and Asia, and also in the southern hemispheres. So larger sea ice extent which has retreated. So sea level would have been 130 meters lower, as you can see here in the last glacial maximum. So more ice, lower sea level, because water from the ocean is evaporated and locked up into glaciers and so on. This sea level change also matters for how much of the calcium carbonate gets sequestered, in addition to how much area is really involved in the glaciation, in the calcium carbonate formation by the phytoplankton itself. Okay, so it is what the wondrous part of the carbon cycle is, that there are many processes involved. They are all playing a role, and yet overall the global carbon cycle seems to have some kind of a stability on these long time scales.